we present SPLATNet, sparse lattice networks for point cloud processing. Traditional CNNs operate on data that lives in dense regular grid, making it unfit to process 3D data, which is predominantly in the regular format of point clouds or meshes. For example, point clouds, the 3D data representation of interest in this work, are sets of sparse unordered points and are difficult to be processed by traditional CNNs. As a result, most existing methods resort to first pre-processing 3D data into voxel representations or multi-view 2D projections. However, this also brings the problem that these conversions result in artifacts lose some natural invariances present in 3D data and incur memory and computational overhead. In this work, we propose a generic and flexible neural network architecture that operates directly on point clouds and alleviates the aforementioned issues. Our architecture also allows seamless integration with 2D data when the input point clouds comes with some associated images.
We first reviewed the operations in a bilateral convolution layer, or BCL, and its favorable properties for point cloud processing, and will then proceed to explain how we build our deep architecture with BCLs as building blocks. For a point cloud with endpoints, the inputs to BCL consist of two sets of features: input features P and lattice features L. Input features P can be low-level features such as RGB colors and can also be high-level features generated by previous neural network layers. Lattice features L defines the lattice space in which convolution will operate. For standard 3D spatial filtering of point clouds, L is given as positional features XYZ at each point. BCL has three processing steps that works as follows. In the first step, splatting, BCL projects the input features onto the grid defined by the lattice features via barycentric interpolation. Following earlier work, we use a permutohedral lattice instead of regular Euclidean grid for efficiency purposes. Once the input points are projected onto the lattice, BCL performs standard convolutions on the interpolated signal with learnable filters. In the last step, slicing, the filter signal is mapped back to the input points via barycentric interpolation. The resulting signal can be passed on to other BCLs for further processing. In summary, BCL smoothly map given input points onto sparse lattice, perform standard convolutions on the sparse lattice, and then smoothly interpolates the filter signal back onto the original input points. It provides a systematic way of filtering unordered input points while enabling flexible specification of underlying lattice structure.
With BCLs as building blocks, we propose a new neural network architecture, which we refer to as SPLATNet. We illustrate its use on the application of 3D point cloud labeling. We're given a 3D point cloud. The task is to give every point in the scene a label prediction. The network starts with a single 1x1 conv layer. A 1x1 conv layer is a point-wise operation, processing each point separately without any data aggregation. The signal is then passed through a series of BCLs, generating a hierarchy of point features. The output of all BCLs are concatenated together and then passed through a few additional 1x1 conv layers before outputting the final 3D predictions. BCLs are differentiable, and thus the network is end-to-end chainable. When there is not only 3D data, but also some associated 2D images, our SPLATNet architecture allows easy integration with 2D image CNNs for seamless 2D-3D joint processing. 2D images are first processed with a standard image segmentation CNN, whose output is projected into 3D points using a BCL, and then fused with features from the 3D network, finally leading to 3D predictions. Our joint model also outputs 2D predictions from fused 2D, 3D features using another 2D image CNN. The whole network is end-to-end chainable. Details about each computational component can be found in our paper.
We now present results on two tasks, facade segmentation and object part segmentation. On HuMonge 2014 dataset, we achieved state-of-the-art performance on point cloud labeling as well as multi-view 2D labeling. Our method also compares favorably with existing method in terms of runtime, which we attribute to our efficient operations on sparse lattices. Here, we show some examples of our predicted labelings on the point cloud, and some examples on the multi-view 2D labeling task. On the object part segmentation experiment, we achieved state-of-the-art performance in terms of both class average IOU and instance average IOU. Here, we show some visual examples. Thank you.